Hello students, previously we have tried to see about kinematics. We have defined what motion, and we have tried to see about motion variables like distance, displacement, velocity, and speed, acceleration, average velocity, average acceleration, and instantaneous velocity, instantaneous acceleration, and the like. We have also tried to see about the two-dimensional motion, especially we just focused on a projectile motion. So today we'll proceed from that and we'll try to see about circular motion. What is circular motion? Well, circular motion is a two-dimensional motion. Means it has both horizontal and vertical components. But to discuss about circular motion, we should have to see some of the common terms that we use in circular motion. The common terms that we use for circular motion for a given particle having a circular path, suppose here you have axis of rotation, you can take it to be a point. Let's take a point, and suppose here you have a particle here. This particle tends to have a circular path, okay? Therefore, when it has a circular path, we should have to have different terms. We should have to refer to different terms, like angular displacement, angular velocity, or rotational velocity, and the like, angular acceleration, and so on. So first let's try to see angular displacement, or theta. Suppose the particle at this point is try to move and reach here, okay? Therefore, from this axis of rotation to this is radius r. While the particle tends to move and reach here, it covers an arc length s, or call it to be angular displacement s. The radius remains constant from this to this. So while this particle moves from this to this and cover an arc length, it subtends an angle theta. So this angle theta is called angular displacement, and this theta, or the angular displacement, can be measured using degree, or it might be expressed using rad and revolution. And the relation between the angle theta and the linear displacement s is given to be s over r. The arc length, or the linear displacement over radius r, gives us the angular displacement. And angular displacement, its unit can be given as meter over meter. Meter over meter is dimensionless. We can eliminate it, dimensionless, but it has unit known to be radian. 1 rad, it has a relation with revolution. Suppose the particle is moving from this and reach here, it makes one complete revolution. In degree, it's possible to say 360 degree. And in radian, it's possible to express it to be 2 pi rad for one complete revolution. So the relation between revolution, degree, and rad can be given as 1 revolution is equals to 360 degree is equals to 2 pi rad. And the other point is the angular velocity. This particle tends to move on this axis, or on this circular motion, having a tangential velocity, v. At every point it makes tangent, so that the velocity is said to be tangential velocity or linear velocity. Then to find the angular velocity, always angular variables and linear variables or translational variables has a relation with their radius. So angular velocity can be defined generally as the rate of change of angular displacement to that of time t. Angular velocity is given to be the rate of change of angular displacement per unit time t. We know that the standard unit of angular displacement is radian, over time is second. So rad per second is a unit of angular velocity. Tangential velocity can be related with angular velocity. Previously we have said that angular displacement over radius r can be given as angular displacement. The same is true, tangential velocity over radius r is given to be angular velocity. So angular velocity is expressed as linear velocity, or we can call it to be tangential velocity over radius. Angular displacement can be given as linear displacement over radius. And we have also a so-called angular acceleration. So angular acceleration is generally defined as the rate of change of angular velocity. So angular velocity over time t gives us acceleration. angular acceleration, and the unit of angular acceleration is rad per second squared. It's given to be rad per second squared. Okay, this is the SI, or standard unit of angular acceleration. Now let's see about tangential velocity, or we call it to be a linear velocity. Previously you have said that this is v, and linear velocity generally expressed as the change of displacement, the linear displacement over time t. And previously we have seen that from this s can be given as r times theta. Theta is angular displacement, s is a linear displacement, or arc length, you can call it arc length or linear displacement. So the relation can be given as s times r times theta. Whenever there is a change in the arc length, or whenever there is a change in the linear displacement, the radius remains constant. For example, the particle moves from this to this, there will be an arc length s, or linear displacement s. If the particle reaches here, there will be a change of s. S changes from this to this, okay? Whenever there is a change of s, the radius remains constant, but the only change is on its angular displacement. So you can put it as r times the change in angular displacement. So putting this here, r times change in theta over change in t, this rate of change of angular displacement gives us angular velocity, omega. Therefore, previously, as I said, that it's possible to have a linear velocity as r times omega, or omega can be related as, omega is angular velocity, is given to be the linear velocity over radius r. This is how we relate angular velocity and tangential velocity. It's also possible to relate acceleration, tangential acceleration, or linear acceleration. Tangential acceleration is generally defined as the rate of change of velocity over time t. But we have said that velocity can be given as radius r times angular velocity. Whenever there is a change in the angular velocity is equals to r times the change in the tangential velocity is equals to radius times the change in the angular velocity. You can put it here so that you can find the rate of change of angular velocity. And the rate of change of angular velocity is called angular acceleration. So we can put and find an expression here. Radius times angular acceleration is tangential acceleration. So far we have tried to see that angular displacement can be related with a linear displacement as s over radius r. Angular velocity can be expressed as linear or tangential velocity over radius r. And the same is true here. Angular acceleration alpha can be expressed as a linear acceleration or tangential acceleration over radius r. These are the main terms that you use for circular motion. Suppose here you have a particle, and the particle tends to have a uniform circular motion. On this uniform circular motion, we have the angular displacement theta here. Here we have the arc length s and v. These are the tangential velocity and the tangential acceleration. The tangential acceleration, due to the change of magnitude of velocity, can be appear on the tangent along the direction of the tangential acceleration. But the angular velocities and angular accelerations are velocity which are acting, or they are directing along the axis of rotation. Okay, suppose here you have a particle, it tends to rotate, the axis of rotation is through this. So omega and alpha are parameters which are acting along the axis of rotation. Suppose you just turn a screw. For example, if you are turning the screw in this direction, it tends to move downward. So the speed, the angular speed is this way, or along the axis. If you are tending to rotate on this direction, it tends to move upward. So angular velocity and angular accelerations are vector quantities that are acting along the axis of rotation. We can possibly discuss this as well in angular motion in Unit 6, but here you should have to define those terms. And the other important point is the centripetal acceleration, and or sometimes known to be radial or normal acceleration. Centripetal accelerations are accelerations which are acting along the center. For a given circular path, For example, if you take a uniform circular motion, meaning for a uniform circular motion is a particle having a constant speed or magnitude of velocity. Let's say that this particle is moving with 10 meters per second. That is the tangential velocity. So when it is 10 meters per second, at this point it tends to act upward. At this point it tends to act to the left, downward, to this direction, and so on. Okay? The direction changes at every point, but the magnitude remains constant. So for a uniform circular motion, it has a constant speed. Or it's possible to say the velocity is constant with its magnitude, but the direction changes. The velocity is not constant. A vector is said to be constant. For example, here velocity and here velocity. The two velocities changes due to their direction. And we have said that two vectors are equal if they are equal in magnitude and the same in direction. Therefore, the velocity is not constant, but the speed is constant for a uniform circular motion. Due to the change of this direction, there will be an acceleration appears, and that acceleration is tending to act downward or to the center. Okay? This acceleration is known to be centripetal acceleration. So centripetal acceleration is acceleration appears due to the change of velocity in its direction, not in its magnitude. The magnitude remains constant, but due to the change of direction, there will be a velocity appears, and it acts always towards the center or axis of rotation. And from similarity of triangles, we can find it in different books. We can find the expression for centripetal acceleration as v squared over r, where v is the tangential velocity or linear velocity. Okay, we can call it a linear velocity or tangential velocity squared over radius r gives us the centripetal acceleration. It's also possible to correlate with that of angular velocity, because we have said that the linear velocity can be expressed as r times angular velocity. If you are trying to substitute here, the centripetal acceleration AC is given to be r times omega the whole squared over r. So we can find an expression that r times the angular velocity squared. It's possible to correlate with this. And the other key point is, whenever there is acceleration, there will be a force. And the force which tends to act towards the center, the net force which tends to act towards the center, is known to be centripetal force. Okay, suppose here you'd have a particle which tends to move on this circular path. So therefore, this particle has a centripetal acceleration. Due to that centripetal acceleration, there will be a centripetal force. And that force, we know that generally force can be expressed as mass times acceleration. And if the acceleration is centripetal acceleration, so there will be a centripetal force. So mass times centripetal acceleration, or mv squared over r, is the centripetal force, or the force which is acting towards the center. So keep this in your mind. And it's possible to classify circular motion into two, as the vertical circle and horizontal circle. Suppose here you have a particle, you just hold a particle and try to have a vertical circle. Let's say you have a stone, okay, or something with a thread. So if you are trying to move it like this, you have a vertical circle, or you'll form a vertical circle. But if you are trying to hold it and to make it a cone like this, it's called horizontal circle or conical pendulum. Sometimes you call it to be conical pendulum because it forms like a cone, okay? So that is called conical pendulum. The vertical circle and horizontal circle, they do have a different property. On a vertical circle, at this point, when you are trying to hold the particle downward, there is a weight acting downward, mg. It's acting downward, and there will be a tension acting upward. The tension changes everywhere as it moves from bottom to the top. Okay? The tension is maximum at the bottom, then gradually decrease here, and here, and at this point the tension becomes zero. The tension becomes zero. And the object has, this particle in a vertical circle, has different velocity. The velocity both in magnitude and direction changes at every point. At this point, we can have the maximum velocity. Here, maximum velocity and maximum tension. Gradually, the velocity decreases both in direction and magnitude. So that as it reaches here, we have the minimum velocity, and the tension becomes minimum, or the tension becomes zero. The tension T is zero while it reaches at the maximum point. Okay. Therefore, it's possible to determine you can use the general equation T plus mg cos theta mv squared over r to determine the tension or the velocity at every single point. Okay, at every single point. For example, at the maximum height, at this point, let's try to determine the velocity that already mentioned it to be the minimum velocity. At this point, at the maximum point, the tension is zero, or negligible. Okay, while it moves vertically upward, the tension on the string is somehow zero or negligible. Therefore, T is zero. Where? At the top point. And theta, at this point, the angle between the mass and the tension is zero. So cos zero gives us just mg. Okay, mg. Then mg is equals to the mass velocity squared over radius r. Mass will be cancelled by mass. Therefore, the velocity at the maximum point, we already mentioned it to be the minimum velocity, and that minimum velocity can be given as the square root of the radius of the circle, the vertical circle, times gravity. Okay, keep this in your mind. This is the minimum velocity where we determine on a vertical circle at its maximum point. At the minimum point, we can determine the maximum velocity, and the maximum velocity, if this particle is free from external factors, free from different factors, it's possible to use the law of conservation of energy so that you can determine the maximum velocity as square root of the minimum velocity. It's possible to use the mechanical energy conservation at this point and at this point. Okay, we may try to see this on work, energy, and power concept. So the main point about the vertical circle is the velocity changes both in magnitude and direction. We can possibly find the minimum velocity at the top. The tension at the top is zero, and we can have the maximum velocity at the bottom. The tension is maximum at the bottom. These are the key points about vertical circle. Now let's try to see about horizontal circle. For horizontal circle, for an object having horizontal circle, we can see different, or can have different example. One of the most example is conical pendulum, as you see here, and the motion of satellites is considered to be a horizontal circle, and motion of banked surface and so on are considered to be horizontal circle. Here we'd have a conical pendulum, means you just attach a string and a mass here. At some angle, you just try to make a cone, okay, a conical pendulum like this. So it forms a tension T here, and the tension T, here we have an angle theta. The vertical component of the tension, let's call it to be Ty, okay? And if for two parallel lines, and if the angle is here theta, it's also possible to have the angle theta here by by alternate interior angle. It's possible to have equal vectors, here theta as well as theta. So the tension has a vertical component T. Since the angle is from this, it's possible to say Ty to be T cosine of theta. Cos, because the angle is adjacent to this, T cos theta, the vertical component. And that is balanced by mg. The object attached here as a mass, so mg, the weight is equals to that of T cos theta. And the object has a tangential velocity. Due to that tangential velocity, m, since it has mass squared, mv squared over r has a centripetal force, okay, centripetal force. And the force which tends to act towards the center is known to be centripetal force. Previously we have said that centripetal force, and that centripetal force appears due to the horizontal component of the tension. The horizontal component of the tension, which is this one means this one, and this one is opposite to this angle, so Tx is given to be T sine theta. The opposite of this angle is sine. T sine theta is the force, the net force, which tends towards the center. And the net force which tends towards the center is known to be or equals to that of the centripetal force. Okay? And the centripetal force is counterbalanced by the tangential velocity. We can have it to be mv squared over r. And the force component which is acting towards the center is t horizontal, so t sine theta. Therefore, taking these two equations, t vertical is balanced by mg. Here you do have tx. T sine theta is counterbalanced by the tangential velocity. But the vertical one, t cos theta, is counterbalanced by mg, or the weight of the object. Therefore, taking the ratio of these two, t sine theta over t cos theta, we can eliminate t sine theta over cos theta gives you tan theta, v squared over rg. So it's possible to find this tangential velocity on a conical pendulum as v is equals to root of rg, okay, tan theta, where theta is the minimum angle that is formed by the cone. Okay, as the conical pendulum is turning or to form like this, there should be the angle theta. In that angle theta, tan theta times rg gives you the minimum velocity, the velocity in which it tends to rotate, and it's known to be conical pendulum. The other applications of horizontal circle is motion of satellites. Okay, satellites there are different natural or artificial satellites actually, but here we are talking about the artificial or man-made satellites. Suppose a satellite is launched from the surface of the Earth and reaches at certain elevation. Let's say that it's reached here, okay, and it tends to rotate about the Earth, So the satellite is found at elevation h, at height of h. But the Earth itself has its own radius from the center of the Earth. The center of the Earth is found just at the core. Okay, the inner core. From the inner core to the surface has radius of the Earth, and that radius is 6,400 kilometer. From the center of the Earth to the surface, 4,600 kilometer, and the satellites are launched at elevation h, at height of h. So, if these satellites stay there, there will be an attraction force between the satellite and the Earth. The satellite has its own mass. The Earth has mass of the Earth. Actually, mass of the Earth is 5.9 something in the power of 24. Okay, so Earth, and there is an attraction force between massive bodies. This is known to be universal gravitational rule. Therefore, this object tends to move downward between the force that is made by these two, and this force is known to be universal gravitational rule, g times mass of the satellite, mass of the Earth, over radius squared. In this case, the radius is from the center to the surface. Here you have radius of the Earth plus the elevation. Okay, you can have r squared in this case, but note that r means radius of the Earth plus the elevation. Okay, the elevation of the satellite. So this is how we determine g mass 1 mass 2 over radius r squared, but the force between the two bodies, the mass of the satellite and radius of the mass of the Earth, can be given using this one. And r is the combination of radius of the Earth and elevation. Keep this in your mind. If there is an attractive force, the force is all due to the downward gravitational force of this massive body. This object tends to move gradually to the Earth. If this satellite is not in a state of motion, okay, let's say that it's just kept there, but gradually it's going to move downward if it is not in a state of motion. Then let's try to determine the gravity at a given elevation. It's possible to find gravity at a given elevation h. So the downward force of the satellite, here the downward force of the satellite is due to mass times gravity, and the interaction between these two bodies is due to the gravitational force. So we can equate these two equations. mg is equals to g times mass of the Earth, mass of the satellite. So we can cancel out the mass of the satellite. So g is equals to, capital G is universal gravitational constant. It's given. Mass of the Earth is given. Radius of the Earth is given. These quantities are well known. The only thing it differs is the elevation. So h squared. As the elevation changes, the gravity also changes. So depending on different elevation, or depending on the elevation where the satellite is found, it's possible to find this gravity G. This gravity G at the surface of the Earth can be determined as elevation is 0. To find G, let's say that it is G naught, the original gravity, G naught. G naught is the gravity on the surface of the Earth. That means when H is 0, if you eliminate H is as 0, the only parameters that you find for G is capital G, mass of the Earth, over radius of the Earth, plus H is 0, the whole squared. So if you have tried to determine this, you can find it to be 9.8. 9.8, approximately 10 meter per second squared. Now the satellite tends to rotate about the Earth. Look here. A satellite is tending to have a circular path, a horizontal circle. Therefore, this circle, this velocity is known to be orbital velocity. Previously, we are assuming that the particle stays there, but now it tends to rotate about a circular path. So how do we determine the orbital velocity? Well, to determine the orbital velocity, since we have tangential velocity, due to the change of direction, every time it changes its direction, but the magnitude remains constant. Therefore, due to the change of direction, we have said that there is an acceleration which is acting toward the center. That acceleration is known to be centripetal acceleration. Therefore, equating these two equations, the centripetal force, which is due to the tangential velocity, and it's given to be mv squared over r. And we do have a gravitational force, g times mass of the Earth over radius of the Earth plus h squared or r squared. So equating these two equations, it's possible to find the tangential velocity. And that tangential velocity for satellites is known to be orbital velocity, orbital velocity. So this is how we determine the orbital velocity. If you are trying to put your satellite, like that we launch our own satellite, ITRAS-1, soon after we are going to launch lots of satellite, I hope. So if you are trying to put your satellite at some elevation h, the orbital velocity should be given g times mass of the Earth, radius of the Earth. The only variable change is the elevation h. So keep this in your mind. This is how we determine the orbital velocity. So far we have tried to see about circular motion. Circular motion has a different application like conical pendulum. We have also a vertical circle, and also have tried to see about motion of satellite. And at last, let's try to see about relative velocity. Relative velocity is a velocity expression of velocity with a moving object. So far, we have tried to discuss about the motion or the velocity or the acceleration of something with a frame of reference at the ground. A stationary frame of reference tells you the velocity of a given object is this one and this one. But now we are trying to see about the velocity of something with respect to another moving object. Okay? So let's take here that two particles or two objects are in a state of motion. Car A, let's say it is car. Car A is heading in this direction with velocity VA. And let another car is moving with a velocity VB in this direction. So to determine the relative velocity of one car expressed by the other car, or let's say that the driver on this car trying to describe the velocity of this one, or vice versa. Therefore, from vector quantity, you have learned that it's possible to determine the resultant of these two vectors. Here, the velocity of B, and let's assume that this is P. The velocity of B plus P gives us the resultant of VA. Okay, P plus VB gives you the resultant velocity A. If you are trying to move this in this direction, P becomes velocity A minus velocity B, meaning the relative velocity of car A expressed by the driver or an observer on car B can be expressed as VA minus VB. This means this is known to be the relative velocity of car A with respect to an observer on car B can be given as the velocity of A minus velocity of B. And keep that it is expressed in terms of vector. This is a vectorial representation. Okay? Whenever you use vector, you should have to note about every I, j, k in the unit vector notation form. You should have to recall that. It's also possible to change this one. For example, if I change this to this direction, the resultant now is VB, okay? The velocity VA, this should be VA, and this is P. VA plus P should give us VB. If you are trying to move this in this direction, VB minus VA, it gives you like this. Therefore, the difference of these two is telling us the relative velocity of car B with respect to an observer on car A. Okay, it's possible to have VBA like this. The relative velocity of car B with respect to an observer on car A can be determined using this. This is a general equation. This general equation can be used for different cases. Suppose here, let's take two cars. They are heading along the same direction, or they might head along opposite direction, or they might head at some angle, or they might heading perpendicular to each other. So keeping the general equation, let's say that this velocity, the relative velocity of car A with respect to B can be given as the velocity of A minus velocity of B. This is a general expression. Let's assume that two cars are heading along the same direction. Car A is heading with 10 meters per second due east. Let's say that this is in this direction. And again, let's take another car. Car B is heading with 20 or let's say 15 meters per second due east again. Both are acting due east. So what you should have to do is always try to represent your equations using unit vector notation form. In this case, it's possible to represent VA vectorially as 10 i's, okay? 10 in I, since it's acting along x. And this one, the velocity, the relative velocity of B is 15 meters per second. Again, since it is acting due east, you can use I. So what is the relative velocity of car A with respect to an observer on car B? If you have such an equation, you just put VA minus VB. And you should have to put it vectorially. Therefore, car A is 10 in I minus car B is 15 in I. Both are acting along I. Therefore, we can subtract these two, and this gives you minus 5 meters per second in the I. Meaning, it is 5 meters per second along the negative I. The negative of I means I is acting along the positive x-axis. The negative of I is acting along the negative x-axis. Meaning, if I represents east, the negative of I represents west. Therefore, the relative velocity of car A with respect to B is 5 meters per second due, the opposite of east is west, due west. You can represent this. Okay, you can have the difference of these two. Now, if I say car A is heading 10 meters per second due east and car B is moving 10 meters per second due west. If I give you like this, if car A is heading, if B, the velocity of B is 15 meters per second, but if it is heading due west, the only thing that you should have to is 15 meters per second. West is the negative of I, because we have represented I to be east. The negative of I, you can put it like this, and put it like 15 meters per second I. The negative of 15 meters per second in I. Therefore, the relative velocity of car A with respect to B, the general equation is given to be VA minus VB. Now, when you are trying to substitute, it is acting 10 in the I minus the velocity of car B is negative 15 in the I. Okay, both are acting I. So we can add these two. When you add these two, you can have it to be 25 in the I. The relative velocity of car A with respect to car B can be determined to be 25 in the I. The vice versa is also possible. It's possible to find the relative velocity of car B with respect to car A. Therefore, the negative of 15 in the I minus the negative of 10. It's also possible to use this one. And it's also possible to use I and J. If the car is heading due north, you should have to put J. And the resultant should be 10 squared plus 15 squared. This should be the way that you should have to use. and I wish you will try to solve lots of problems. So this is all that I've got for today. Next time we'll try to see about dynamics. So far we have tried to discuss about kinematics. So next time we'll try to see about dynamics. So goodbye.